Welcome to lecture number 9. In this session we are going to put together a business jet once again from scratch. This will be a completely independent model of the brand new Dassault Falcon 10X project, based exclusively on minimal early specifications released by the manufacturer in May 2021. The geometry of the aircraft has been estimated from a selection of published views, and I will show you how later on. Let's start piano. Experience with other planes in the piano database will help us to assign parameters. I will point out similarities and differences in the settings we choose for the business jet compared to the commercial airliners that we have looked at so far. And I will also say a few words about uncertainties. If you're a piano user, you might want to pause, rewind or review past material at any point. Otherwise, you can just listen casually through the narration. We will launch straight into our definition. Set masses to imperial, new plane palette, 8 passengers in something like an NBAA club seating setup. I estimate external fuselage width at around 2.96 meters, broadly compatible with the quoted internal cabin width of 2.77. Seats abreast is 2. For the fuselage, I will reuse existing shapes from the Falcon 6, obviously rescaled to 10x dimensions. This time we'll split the fuselage mostly into front and rear sections, leaving only a little bit in the middle. Let's look at the shape in the shape editor. So this front fuselage shape includes the forward portion of a wing body aerodynamic fairing. I can load the shape from here, or I can do it directly from the names palette. Fuselage length is about 29 meters. I will set the component lengths, and in the rear I will put 10 meters, 13 meters at the front, and the mid fuselage is then 29 minus 10 minus 13, 6 meters. MTO mass is given us 115,000 pounds. To start with, I will just enter some order of magnitude guesses for the wing area and the aspect ratio. Let's put in an aspect ratio of 8 and a wing area of 100 square meters. We could have estimated the wing area, say, by assuming 80 to 90 PSF as a typical wing loading. So if I do 115,000 pounds divided by, let's say, 85 PSF, that gives me about 125 square meters. Alternatively, from the stated span of 33.6 meters and say a typical aspect ratio of 9, we get span squared divided by 9, 125 square meters. In fact, the only planform picture that has been published at low resolution does indirectly suggest an Airbus reference area close to 125 square meters. But remember that our input parameters for the wing are trapezoidal. In a moment, I will set out the overall layout of the wing planform, and after that, it will be possible to adjust the wing size to match any other wing area definition. Sweep back 35 degrees. You may recall that the 787 also cruises at the typical Mach number of 0.85 with only 32.5 degrees of sweep. However, the Falcon 10X also has to do well at Mach 0.9 and even beyond that. Thickness chord 13%, taper ratio about 0.22. The MMO is given as 0.925. And we'll put a nominal design cruise altitude of about 41,000 feet. Nacelle width around 1.95 meters. Engine thrust. The engine manufacturer only states that the engine sits in the 18,000 to 20,000 pound thrust bracket. And for now I will pick a value just over 18,000, let's say 18,250. No nacelles mounted on the wing, and on the fuselage about 10% clear of the fuselage expressed as a fraction of the nacelle width. So we enter 0.1. We've entered all the vital parameters, and let's try and take a first look at the aircraft. No nacelles are allowed on the fuselage when the stabilizer mounting is low. So parameters with stabilizer mounting, set it to high, and try again. So as before, we'll go through the basic components: fuselage, wing, nacelles, tail. I will increase the fuselage depth and extend the cabin into maybe 70% of the front fuselage and something like a quarter of the rear fuselage. So fuselage depth over width, set it to 1.1. Cabin in front fuselage 0.7, and cabin in rear fuselage fraction 0.25. Floor location, we'll lift it up a little bit to 0.3. Give it a nominal seat pitch of 2 meters, and we can increase the seat width and aisle width. So let's say 0.65 meters and 0.65 again. Let's put in the right number of windows for aesthetics. So the fuselage is already about right. Nacelles. Length over width, increase it to about 2.8. And nacelle location on fuselage. This distance as a fraction of the nacelle length. About 1.4. And nacelle name, I will use this generic 2 shape. So these nacelles line up nicely with the rear bulkhead. Tail geometry, I will move the fin a little bit forward, and this is 1 meter over here, so I'll move it forward by about 0.7 meters. Fin tail cone gap 0.7. For the tail volume coefficient, so V bars, I will use 0.7 for the stabilizer and 0.05 for the fin. The stabilizer aspect ratio I will leave at 5. Sweep back around 30 degrees for the stabilizer, maybe just a touch more, but I will leave it there. Stabilizer thickness chord, let's reduce it to about 9%. Stabilizer taper 0.5. The fin shape is complex with a large top fairing for jacks and stabilizer trim mechanisms, but in broad terms, fin aspect ratio is around 1 and fin taper ratio around 0.8. Fin sweep back 45 degrees and 9% again for the T over C. For the trim and balance, I will set a minimum static margin of just 3%, similar to our choice for the 787. Now, with aft-mounted engines, any fixed equipment will be placed as far forward as practicable. Also, for smaller aircraft types, the cockpit tends to contribute proportionately more in the same direction. So I will set the fixed equipment CG fraction somewhere between 0.4 and 0.45 compared to the 0.5 that we use for the 787 and the A350. So let us say 0.4 plus 0.45 divided by 2, 0.425. Look at the aircraft. Wing geometry. Planform brake fraction at 0.35. Planform brake trailing edge adjustment. .45. We've put in 13% for the thickness chord at the root, and at the break point I will estimate around 10.5%. So we want to enter 10.5 divided by 13. And for the tip, just 7.5%. So 7.5 divided by 13 again. Dihedral, just 1 degree nominally. A bit of twist, -3 degrees. And we'll have winglets. These are in reality curved winglets, and we will approximate them the way that we did in the A350. So span ratio of 0.1, cant angle of 45 degrees, and occupying the full chord. For the undercarriage, we'll just shorten it a little bit and bring it inboard. Length below fuselage, let's reduce that to 1.4. And ETA undercarriage, a bit less than 10%, let's say 0.08. So we've now finished our major geometric palettes. And so far we have disturbed 40 parameters. Having defined the wing layout, we can now resize the wing. Using an Airbus definition, we'll put in 125 square meters and a span of 33.6. Let's look at the geometry. Now, geometric fuel capacity is a key issue for business jets. Manufacturers will try to maximize it as much as possible. The black region is the wet portion of the wing, and at the moment that is about 27 cubic meters. We can space out the spar locations at the root a little bit, move the front spar forward and the rear spar slightly backward. So fuel capacity, XI, which is the chord-wise location, front spar at the root 0.1, rear spar at the root 0.7, and of course the root location is the more important. And looking at the basics again, we now have about 31 cubic meters. Let's also set the fuel density at 6.7 pounds per US gallon. The manufacturer publishes a maximum fuel weight of 51,700 pounds. So from that we can set the capacity. As 51,700 divided by 6.7. And that gives us 29.2 cubic meters. I will say more about fuel capacity a bit later on. 44 parameters disturbed so far. The geometry is now pretty much fully defined, except for the exact wing location along the fuselage, and I'll finalize that later, after we have set the known weights quoted by Dassault. Let's now go through all the palettes from top to bottom. Basic sizing, nothing to do. CD0 and CDI. We expect to achieve a significant degree of laminar flow compared to the large commercial jets that we have looked at so far, partly because of the smaller dimensions and higher altitudes, which reduce the Reynolds number, and partly because of the very high quality of surface finish in these premier business jets. I will set the wing transition at 30% of the chord. This is just an effective value that would in reality vary across the span. You could think of it as an indication of aerofoil technology level. Similarly, for the fuselage, I will set the transition at 10% of the fuselage length. I will apply an induced drag factor of 0.97 as before, and when I say as before, it just means that I've used something similar during previous lectures. And also set the windscreen frontal CD to 0 as before. I will apply a nominal user adjust CL/CD curve similar to lecture 6, except now centered on a CL of 0.45 instead of 0.5. So 0.45, 0, 0.55, 2 drag counts, 0.65, 10 drag counts, and 0.35 symmetrically. So now we're assuming a slightly lower typical design CL, bearing in mind wing loadings will be lower. Also, in the case of a business jet, we don't want to tune the design too much for a single cruise CL and Mach number, as we might do for a 787 or an A350. That is because we now have to balance an optimum with a desire to retain adequate performance at higher speeds like Mach 0.9. Compressibility method, RR adjustable as before, rooftop end 0.67. There will be a lot of drag uncertainty near the very high MMO of 0.925, and I will set the CD0 compressibility factor to 1.15 compared to the 1.1 that I used in previous commercial planes, and start at Mach 0.8 as before. This time we will leave the empirical compressibility coefficient 2 at its default, and we won't even try to guess any adjustments for Mach CD curve. Engine. I will load the large bizjet fan 10s. This is a generic model of a modern business jet engine. It is not based on the Rolls-Royce Pearl 10X or its predecessors. Choosing a reference condition of 45,000 feet and Mach 0.85. Max cruise SFC is 0.6512. I will adjust it to a reference value of 0.62. This is just an estimate which I believe to be reasonably close to industry expectations for the Pearl 10X. So we'll apply a user factor on SFC of 0.62 divided by 0.6512. Let's call it 0.952. Fuel capacity we have done already, and fuselage geometry. High lift devices. Aerofoil CLmax of 1.3 as before. A typical double-slotted Fowler flap for Dassault. 15 degrees for the takeoff. Say 35 degrees for the landing. We'll set the slat exposed span fraction at 0.85. Inboard slat coverage is less important than outboard. Takeoff palette. Business jets have high thrust to weight ratios and can accelerate fast even with one engine out. If V2 is set at its lower bound and the pilot executes an over-aggressive rotation to meet a difficult UFL target, it becomes possible for the wingtips to stall in ground effect. This can lead to loss of control and has happened during flight tests of another type. Now, the presence of slats in the Falcon 10X makes this scenario very unlikely. Even so, I will be conservative and set V2 a little bit higher than I did in previous examples. Instead of 1.13, I will set it halfway between that and 1.2. Landing palette, approach speed ratio of 1.23 as before. Mass per passenger of 200 pounds, which is the normal NBAA assumption. Maximum payload over design payload I will set to 4, typical of business jets, and given their very small nominal payloads, it could be even higher. Maximum landing mass ratio as the ratio of MLW to MTOW I will set to 0.76. There is no need for it to be high, except perhaps for operational flexibility in cases of unrefueled multiple hop flights. We'll set the furnishings mass per passenger to no less than 500 pounds per passenger, about 226 kilograms. Compare that to 85 kilograms in the 787 and A350, and it could easily be more than that. Number of flight crew set to 3. And I will set a nominal ramp increment of 400 pounds from the quoted maximum ramp weight. 66 disturbed parameters so far. Mass per power plants, we won't change anything. Structure and systems, choosing the same wing mass method as before. And we can in fact load the standard method's preferences. So all our settings are now as before. Miscellaneous, user limited MMO 0.925, and we will assume a VMO of around 370 knots calibrated. Nacelle, nothing to change. Names of linked files, nothing. New plane, DOC we are not using. Pressurization, maximum operating altitude of 51,000 feet. And a corresponding cabin altitude of about 5,100 feet. Reserves, 200 nautical miles diversion, 30 minutes hold and 0 contingency, which is NBAA IFR rules. Let's set 1,500 feet for the hold altitude. 5 minutes taxi out. Just 1 minute for the takeoff, 3 minutes for the approach, 5 minutes for taxi in. Tail, takeoff, undercarriage, untitled palette, user factors, and wing geometry. We do not need to change anything in any of these. So now we have a total of 80 disturbed parameters. And let us go ahead and set the exact quoted weights. We have an MTOW of 115,000 pounds. The OEW is given as 61,300. The maximum payload is given as 6,500, so MZFW will be 6,500 plus the OEW. And MLW somewhere around 87,500 pounds. This is our aircraft. Let us fix the wing location. It's about 0.375 and free up the fixed equipment CG fraction. (81 parameters disturbed). Let's look at our weight breakdown. At the published weight figures, the aircraft is very marginally fuel capacity limited, in the sense that OEW plus standard payload plus maximum fuel is less than MTOW. Operational items is what piano adds or subtracts to match the target OEW. In this case, only a minimal weight adjustment was needed. This is not necessarily an indication of great accuracy in weight estimation, however. The balance between structure and furnishings weight is not known. We only have the manufacturer's expectation of OEW. For example, I did not apply any weight factors on the structural components. It could be that the composite wing is lighter and furnishings are heavier, or perhaps that Dassault choose to focus more on the aerodynamic benefits of thinner wings and less on the weight reduction. Let's look at geometry and our 3 view again. For a bit of perspective, I will just remind you that the overall span and overall length are the only numbers that have been explicitly stated by the manufacturer. So let me now clarify a little bit how the geometry was estimated. This is our current planform view, and this is the same picture. Most of the geometry is derived from a single low-resolution view that is included in the manufacturer's release. This is a provisional overlay based on that view. If its proportions are corrected to match the published dimensions, the low-resolution planform is consistent with high-resolution images of the cabin and with other information in the marketing material. Even so, everything you see here remains an assessment of the geometry and is not the manufacturer's position. So we have the piano view, the low-resolution overlay, a cabin overlay, some known dimensions, some clear match points between low resolution and high resolution, and piano view again. So finally, with our aircraft now fully defined, we can set the range modes. I will set Mach 0.85 and assume mixed flight levels at 2000 foot intervals. And we can save our plane on file. Lecture 9 F10X. And we can reload it at any time from here. So the modeling of the aircraft is complete, and we can now start looking at the predictions of performance and other characteristics. Our design range is essentially 7,500 nautical miles, and that matches the manufacturer's target range. We can also build up a detailed mission sequence corresponding to our range calculation. So 7,498 nautical miles within 5 nautical miles. And we can rerun through it step by step and try different options or make any changes as we did in lecture 4. This is our climb, and we can rewind, try a different climb schedule, 260 knots, up to Mach 0.85. And then climb up to 41,000 feet. And we could continue like that through the entire profile. I'll cancel out. Take a look at specific air ranges. Let's say at 41,000 feet. Altitude versus mass. This time our ceilings and our optimum are quite close to each other, and they're typically a lot higher than those of airliners because of the low wing loading and high thrust to weight ratios of business jets. Payload range. Design range is fuel capacity limited as expected. Flight envelope, let's say at a weight of 100,000 pounds. So we can see that between, say, 30,000 and 40,000 feet, we can reach or exceed Mach 0.9, which is the light grey line here. We can get some perspective on the design balance between engine and airframe by looking at the cruise SFC loop and lift-to-drag ratio. Say at 45,000 feet. This is our SFC. This is our L over D. In this case, the thrust near the bottom of the SFC loop and the drag at the peak L over D line up nicely. Let's try out some slight variations to reflect uncertainties in engine and airframe performance. At 45,000 feet and Mach 0.85, our spot SFC is 0.62. I'll set that to 0.625. So I take the existing user factor on SFC, multiply by 0.625 and divide by 0.62. For the aerodynamics, I will also go and change our wing transition assumption. Let's say from 0.3 to 1/3. Look at the range. It's basically unchanged, so the two balance out. Now, some level of uncertainty is always present. Even flight-tested performance numbers are themselves subject to significant interpretation. So fine-tuning the balance of assumptions like this can be argued differently between airframers and engine manufacturers, and that is a common situation. In previous lectures with the 787 and the A350, we applied direct user factors to match precise targets, for example in terms of the range. We can also fine-tune our assumptions like this to the extent that we feel confident about specific knowledge or experience from related airframes or engines. Let's get back to our original aircraft. The original SFC factor and the original wing transition. Take a look at the lift drag polar. Let's say at 45,000 feet, and I will add the MMO as well in the list of Mach numbers. It is worth emphasizing that although aerodynamics and performance predictions at normal cruise conditions tend to be very good, at the maximum Mach numbers, near MMO, the uncertainties are always much greater. The manufacturer will have some better indications of the shape of the drag polar at these conditions through detailed three-dimensional computational fluid dynamics. But even with CFD, uncertainties in the drag levels near MMO will still remain high until flight testing gives a better picture. Let's change our range modes and set a cruise Mach of 0.9. Our range is down to 6,135 nautical miles, and we are now starting the cruise at 37,000 feet. I will make a slight change to our user adjust CL/CD curve, and I will increase the drag levels at the lower CLs. So at a CL of 0.35 I will go from 2 drag counts to 5. At 0.25 I will go from 10 drag counts to 15. Let me flatten the slope at that point as well. 0.451 and 0 again. And now if we fly at Mach 0.85, our range is barely affected, 7499. But if we fly at Mach 0.9, we're down to 6,034 nautical miles, so we've lost 100 nautical miles. In fact, an uncertainty of 100 nautical miles at Mach 0.9 is not bad. 500 nautical miles or more would be quite common at this early stage. After all, flying at Mach 0.92 and at low weights, we could expect that significant portions of the airframe will be producing negative lift. Let's get back to our original. Let's run mission at range, say 3,000 nautical miles. Our block fuel is 17,900 pounds. Change our range modes, Mach 0.9. We could change our climb and descent schedules as well. Let's set 260 knots, Mach 0.85. Fly the mission again. And we are up to more than 21,800 pounds for the same distance. Let's run it at 500 nautical miles. £4,500 of fuel. Our takeoff weight is a bit more than 70,000 pounds. If I look at the flight envelope, at a weight of 70,000 pounds, we could get some of the highest Mach numbers at around about, let's say, 36,000 feet. So if I set maximum speed and flight level 360 only, and let's use 300 knots for the climb, followed by Mach 0.9. Fly the mission again. So our fuel burn for the 500 nautical miles has now gone up to 6,036 pounds. Our block time has reduced from 82 to 78 minutes. So that wouldn't be a very good trade-off between time and fuel. Again, it would be easy to build up these missions as maneuver sequences and vary all kinds of flight profile options like we did in Lecture 4. Now let's look at takeoff and landing field performance. Dassault simply claims a TOFL of less than 6,000 feet and a landing distance of less than 2,500 feet. We can examine some TOFL plots. At ISA plus 0 with flap 15, takeoff mass and TOFL at different pressure altitudes. The red one is sea level. So at sea level and with a 5,000 foot runway, which might, for example, be London City, we would be limited to a weight of something like 107,000 pounds. Run it again at ISA plus 15. So for a 5,000 foot runway at sea level, our limit weight drops down to something like 104,000 pounds. If I increase the flap a little bit to 20 degrees and run it again, we can improve the weight to 105 or 106,000 pounds, but we are getting close to regions where climb gradient limitations are forcing us to reduce flap. Let us assume that certification tests are going well and we choose to reset the V2 ratio from our current value of 1.165 to 1.13. Run TOFLs, ISA plus 15 and flap 20 again. So now we get to something like 109,000 pounds, but our gradient limits are very close, so we could really do with more thrust at this point. Let's go to our engine, which is currently 18,250 pounds. I will boost the takeoff rating through the user factor and takeoff rating. 20,000 pounds divided by 18,250. So that's just under a 10% thrust increase. Run again at ISA plus 15 and flap 20. So with 20,000 pounds of thrust, we are just about capable of taking off at full MTOW from London City with a 5,000 foot runway at sea level and ISA plus 15. And that is certainly an impressive level of field performance. Looking at the pressure altitude of 8,000 feet, which is the light blue line, we can take off at MTOW from an 8,000 foot runway. We are gradient limited, so flap will be less than 20. And if we run it at 15, we can indeed take off from an 8,000 foot runway. A pressure altitude of 8,000 feet corresponds to a higher geopotential altitude. At ISA plus 15, geopotential altitude is more than 8,400. And that means that we have more than enough performance to operate from Aspen, Colorado, where the local airport is Sardis Field at an elevation of 7,800 feet and with a runway length of just over 8,000 feet. But remember, we are now using 20,000 pound thrust engines to do that. Let's look at the weight, altitude, temperature limits. What limits at different ISAs? Flap 15. This particular engine model is flat rated to ISA plus 15 at sea level, tapering back to normal by around 6,000 feet. At ISA plus 15 and 8,000 feet, there is no weight restriction. We are above the MTOW. For landing, at our estimated MLW, at an altitude of 8,000 feet and ISA, we see something like 4,600 feet for an LFL requirement, and the landing distance would be just 60% of that. So we have now taken a good look at the anticipated performance of the 10X. Let's move on. So far in this session, we have treated the Falcon 10X as a strictly fixed point design, as defined by Dassault. I will quickly run a very simple sizing and optimization exercise just to demonstrate how we might get close to the key numbers of the F10X directly from the specification requirements. Business jet design scenarios can differ from those of commercial airliners in many ways. The airframer may want to freeze the nacelle size and nacelle contours because of drag and area ruling considerations, and it is possible to vary engine thrust to a reasonable extent within a fixed nacelle. So this time I won't use any nacelle scaling. I will simply free up the OEW, and then I will radically change our starting point. Let me just pick some wild initial settings for the basic sizing parameters. MTOW 80,000 pounds, thrust 8,000 pounds, wing area 80 square meters, aspect ratio 8. So our initial design does not even need to be feasible. It may not even be able to take off, let alone cruise. So let us start the optimizer. Our variables, MTOW, wing area, thrust and aspect ratio. Our constraints, 7,500 nautical miles, 6,000 for TOFL requirement, and for the landing field length we'll put the quoted landing distance, which is 2,500 feet, divided by 0.6 by definition. And we will use minimum fuel as our objective function. Let's start. So I've let this run for 2 minutes now, and I will stop. This is our aircraft. It has, as usual, been saved as opti-after. So 7,500 nautical miles. Notice that our fuel capacity constraint is active. Available over required fuel is 1. And TOFL and LFL landing distance are close to being active, but they're not quite active. So let us compare our Falcon 10X and the opti-after. Lecture 9 F10X, opti-after, choose Airbus wing area and available thrust. And as you can see from all the numbers here, the opti-after solution is very close indeed to the actual F10X. Payload range diagrams, fuel capacity limited at this point. Without showing you yet another optimization run, I'll just mention that if we had targeted minimum MTOW instead of minimum fuel, we'd have been able to shed around 2,000 pounds of weight with a reduced wing area and aspect ratio, obviously at some fuel burn penalty. But now TOFL would also have become an active constraint. As always, in reality, many complex judgments have to be made when making sizing decisions. But even so, we can see that we can get to the right overall numbers for the F10X nicely and quickly. Let me say a few final words about fuel capacity. Once again, for this class of aircraft, geometric fuel capacity is critical. We noted good accuracies in our predictions of available capacity for the 787 and A350. But in general, there will be considerable statistical uncertainties until a complete 3D structural model can be produced. Wing interiors have very intricate shapes, particularly near the root, where fuselage or saddle tank contours will vary a lot. What we can say, however, is that there is every indication that this wing is big enough and no fuel capacity problems are expected. In general, we have seen good agreements between the Falcon 10X specifications and piano assessments. During the last lecture, we put together a good model of a state-of-the-art airliner. Now we have a good model of what is potentially the next top-end business jet. So let us take a little step back to look at the big picture. We look at transport efficiency for our nominal missions. So for the A350, our fuel efficiency is around 4.6 ton-kilometers per kilogram fuel. For the Falcon 10X, it is 0.46. In terms of CO2 emissions, the A350 produces 65 grams of CO2 per available seat kilometer. The Falcon 10X produces 625. These differences are in essence one order of magnitude in favor of the airliner, and yet these two aircraft represent very similar levels of our existing technological capabilities. The huge differences are not a matter of abstract metrics or of technology. They are caused by the fact that the two aircraft are designed to satisfy two very different requirements. They effectively operate in parallel universes. All of which begs the question, what kind of picture does the latest global emissions standard paint? That standard is ICAO's CO2 metric, now formally adopted. Given a reliable aircraft performance model such as Piano, the metric is easy to calculate. So, using ICAO's new type rules, and subject to only minor uncertainties in ICAO's RGF reinterpretation of cabin area, here are the numbers. The A350 model from our last lecture passes with a good margin in the region of 6%. The business jet also passes, and in fact it does so with a noticeably more comfortable margin of around 14%. These numbers reveal the sheer scale of the failure of current policies. More explanations are in Lecture 3 and in articles published in piano.aero since 2012. To conclude, in this lecture we have put together a compelling independent model of the new Falcon 10X business jet now under development. The resulting piano definition file contains just 96 parameters and takes up 6 kilobytes. It was finalized within a few days of the first information release from Dassault. And I should mention that putting together YouTube videos like this takes a lot more time than modeling the aircraft. As with previous work, this piano model is transparent and fully adjustable. It can track the future evolution of the Falcon 10X, or it can serve as a template for other business jet assessments. And I will stop here for now.